Alright, so in this video we're going to discuss a couple of other cycles. And we're going to start with an Otto cycle. And I will tell you guys ahead of time, I understand engines in physics terms, theoretically. Please do not ask me anything about your car. I always tell the story about, there's an episode of The Big Bang Theory where they get stranded on the side of the road, they open the hood up. One of them says, "Does anyone understand how car engines work?" They're all like, yeah. Can anyone actually fix it? No, because all they understand is the theory behind them and not the actual mechanics of them. So please remember that I'm a physicist, not a car mechanic. Alright, so we have a pressure versus volume graph here. And we start with a certain amount of gas inside of a piston. And we're going to start by adiabatically compressing that gas from A to B. We're then going to add in heat, so this is where your spark plug comes in. You're then going to adiabatically expand the gas, and then you're going to return it to its original thermodynamical state by expelling waste heat, so QC. Now you'll notice here in this graph, we have volume and then R times volume. R in this case is the compression ratio. And typical compression ratios are between 8 to 10. And we use the compression ratio, and because we're adiabatically compressing and expanding, we're also going to make use of the adiabatic index. So the efficiency is equal to 1 minus 1 divided by the compression ratio raised to the adiabatic index minus 1. In this next section, we're going to discuss the diesel cycle. The diesel cycle is different than the Otto cycle. So from A to B, when we have our adiabatic compression, there's no fuel yet. The fuel is not injected until we get to B. And for B to C, we have isobaric expansion, and then from C to D, we have adiabatic expansion. Now, because from A to B, we have adiabatic compression, we're actually raising the temperature inside of the cylinder so that when you're injecting the fuel, it is at a high temperature and ignites without the need of a spark plug. We're then expanding it isobarically and then expanding adiabatically before then isovolumetrically expelling your waste heat. The other thing that's different between the Otto cycle and the diesel is because you're not injecting the fuel, there's not a chance of pre-ignition, so you can actually have higher compression ratios, which allows for a more efficient engine. So typical compression ratios in this case is between 15 to 20 versus the 8 to 10 we talked about for the Otto cycle. In this next section, we're going to discuss refrigerators. Refrigerators are actually heat engines operated in reverse, which means instead of getting work out of the engine, you actually have to put work into the engine to get it to operate. Now, there's typically coolant in the back of your refrigerator, and the work has to go into first cooling that coolant, which is then pumped through the back of your refrigerator, which absorbs heat, because remember, energy always goes from hot to cold. So that coolant is absorbing heat, which then goes back into the environment and gives off that heat out the back of your refrigerator, which is why your back of your refrigerator is usually pretty warm. Now, you do have to be careful here because the idea of QC and QH are reversed. You're taking energy in from a cold source and giving it to a hot source, because technically the inside of the refrigerator is cold and the outside of the side of the refrigerator is hot. So the concept are a little bit reversed compared to a heat engine. And rather than calculating the efficiency of the engine, we're actually going to calculate what we call the coefficient of performance, which is what K stands for here. So K is the ratio of QC to work, or the coefficient of performance is equal to QC divided by QH minus QC.